right, here we are looking at some homework problems that I'm assigning to my students to go along with our initial look at integrals. And if you have skipped the previous video where I walked through the slides and I'm looking at definitions and some of the problems that the author walks through, I recommend that you go back and even if you can watch the video at 1.5 speed or double speed so you can still see what I'm doing and hear what I'm talking about, there are definitions, there are concepts, there are a couple of processes for sure in the previous video that you're going to want. So this video will definitely help you complete your homework assignment, but especially for those of you who are going to be going on into a Calculus 2 course, you definitely want to have a good handle on these concepts, because while math does move forward and build on itself, it does also grow in depth, and so you will need to have, and you will be required to draw on your actual understanding of the concepts and what's going on behind the scenes in order to solve problems like these and future problems. Okay, so all of that being said, some of the problems excuse me, that I'm going to go through now, I'll go through in various degrees of detail. For example, this one. The question here is to evaluate each integral, and we're going to do that using areas. So remember that the integral is the area under the curve, and oops. Can I zoom in? I can. Oh, but I can't. Come on now. There we go. So this first integral goes from 0 to 10. We're integrating from 0 to 10. Those are your limits of integration. The integrand is the g function. And from 0 to 10, if we look at our graph, what we're really being asked for is the area under the curve down to the positive x-axis. And since we have been given a diagram for this entire curve, or at least the interval that goes from 0 to 35, we can find the area under the curve simply by using geometry. This first area that we need is a triangle. Area of a triangle is base times height divided by 2. So we have a base of 10, and we've obviously got a height of 20. So 10 times 20 divided by 2 is 100. So you could type in an answer of 100 for part A. Part B, here the integral goes from 0 to 30. So it is working with this semicircle. But remember that this semicircle is below the x-axis. And so if we use our typical method where we're integrating and our lower limit, the 10, is less than the upper limit of integration, 30, which it is, and we're integrating a curve, which we can see here is clearly below the x-axis, the area, or the answer to the integral, is going to be negative. So be careful there, and let's see, this circle has a radius of 10. We're going from 10 to 30, which is a total distance of 20. Half of that is 10, so the radius is 10. Area of a circle is pi r squared, which is here, pi times 10 squared, which is 100 pi. We only have half of the circle, however, so we'll divide that by 2, and we get 50 pi, but put some kind of a note, because we're below the x-axis, we do need to type in an answer of negative 50 times pi. And finally, same idea over here for this little triangle. You figure out how wide it is and how tall it is, and do base times height divided by 2 to get your answer for that portion of this question. In number 4, evaluate the integral by interpreting it as a means or in terms of areas. Great. So what you have to do in number 4 is you've got to draw your own picture of, in this case, the absolute value function. Remember that the absolute value function looks like a V. The vertex of it, you could say, is at the origin, and it has a slope of 1 going out this direction. It has a slope of -1 going out this direction, and you're integrating from -1 to +1, 2, 3, 4. So you should be able to turn this into 2 triangles, figure out the bases of them, the heights of them, find each triangle's area individually, and then add those 2 areas together. I think you can handle that. Now, number 5 is not a trick question, although I suppose it could be interpreted that way, but this is a phenomenon that we saw in the notes for this section in 5.2, and we thought, when in the world is that ever going to come up? Well, here it's coming up just as an isolated question. Notice the limits of integration go from pi to pi, which means that the width of each subinterval, in other words, delta x, which equals b minus a divided by n. B and a here are both pi, so delta x equals pi minus pi over n. Regardless of how many subintervals we're working with, or maybe even infinitely many, 0 divided by any positive value is going to be 0. And so as you add up the area of all of those rectangles, doesn't matter how tall they all have a width of 0. And so the area under the curve, in other words, this integral, will be 0. In number 6, we're being given a particular piece of information, and that's going to allow us to use some of the properties of integration in order to solve this statement over here to the right. And the first thing I'd like to do is basically take this integral and distribute it, so to speak, to the 2 terms that make up the integrand. And that leaves us with the integral from 0 to 1 of 4 minus the integral from 0 to 1 of 9x squared. Both of these should have a dx at the end of them because we're integrating with respect to x. So to be thorough and ultimately correct, we should have the dx on both of those. And there's one other property, so that was sort of a distributive property, although it wasn't given that name. That's definitely what it looks like. The next property we use is the one where we're allowed to take a constant value, which was often referred to as a lowercase c, like this 9 here, and we can factor it out, and we'll put it in front of the integral, or on the outside of the integral, so it's going to come out here. So we will subtract 9 times the integral from 0 to 1 of x squared dx. Remember from the previous, or from the video about the notes for this section, that in an integral where your integrand is a constant value, so here we're going integrating from 0 to 1, and what are we integrating? What's our function? It's 4, which is a constant function. So what you're really finding is the area of a rectangle that has a height of 4 and a width of 1 because it's going from 0 to 1. So that is equal to 4, where you could say that it's equal to 4 times 1 minus 0, upper minus lower, minus 9 times, and then what in the world is the integral from 0 to 1 of x squared? Thankfully, that's a piece of information that was given to us. It's equal to 1/3. We've actually investigated that previously. So now we've got 9 times 1/3, and all we have left is arithmetic. 4 minus 3 makes 1. So we'll be able to type in 1 as our final answer there. In number 7, this is another phenomenon that we saw where I drew a beautiful hand-drawn diagram with lots of colors. And then, of course, on the next slide, the author had provided a printed diagram with clean lines and nice shading, but not as many colors as I had used. Notice that here, the question is asking us for an integral that goes from 1 to 3, and we're being given some information. We're being told that the integral from 1 to 5 is equal to 10, and from 3 to 5 is equal to 5.6. I don't know what this graph looks like. I don't really care. So one way that we can look at this is we'll make up our own function, f of x. So there's function f, and we're going from 1 to 5. So this is 5, 4, 3, 2, 1. Those aren't. Get that back there. 5, 4, 3, 2, 1, 0. Okay, that's a little bit closer. One of our integrals is going from 1 to 5, so we need to have the 1 on there. Another integral is going from 3 to 5. Okay, so those are all of our limits of integration. And the full integral, this entire area in here, our first given piece of information tells us that entire area is 10. I wonder. Okay, maybe I should put it out here. There's no great place to write that. 10. The integral that goes from 3 to 5, we need a different color now. Maybe this pink color will work. From 3 to 5, this area is 5.6. So the entire area from 1 to 5 is 10. The right-hand half, so to speak, of that area from 3 to 5 is 5.6. So if the whole thing is 10, and this portion of it is 5.6, and we want to know what is the area under the curve here. It's the missing piece. It's the other half of the area under the curve. It's not half by area, it's only half by interval. And we will be able to do simple subtraction in order to find out that that area is 4.4. So your answer on this one is 4.4. The other way that this concept was demonstrated for us was we saw that the integral from a to c of a function plus the integral from c to b of a function is equal to the integral that goes from the first limit of integration to the last limit of integration, so from a to b of our function. And with the question that we're working on, we notice that the entire interval from a to b is from 1 to 5. So this integral is a 10, the entire area under the curve, and separately from 3 to 5, we were told that this integral, sort of the second half of it, is equal to 5.6, and the unknown part is from 1 to 3, so that's this first integral right here, and that has an area of question mark, or x, and then you have to solve this equation for a question mark, or solve it for x, which means you have to subtract 5.6 from both sides. That's a plus sign, and yet again you find that the area under the curve from a to c, or in this case from 1 to 3, is still that 4.4. Number 8 is interesting. Each of the regions A, B, and C bounded by the graph of f and the x-axis has area 3. So they're saying whether it's below the x-axis or above the x-axis, the true area is 3. And we're supposed to evaluate this integral. Okay? Well, let's keep using this sort of burnt orange color. I like that. The first thing I'll do is distribute my integral. So I'm going to take this integral and I'm going to distribute it to the f of x and to the 2x and to the 3. So we have the integral from -4 to 2 of f of x dx plus the integral from -4 to 2 of 2x dx plus, again, the integral from -4 to 2 of 3. The second two integrals are going to be considerably easier conceptually and arithmetically to figure out. The first one's going to be the tricky one. So I think what I'll do is I might work out the first one, and I'll switch colors. Let's work out this one, and I'll do that work over here, and then I'm probably going to erase what I put over here, and then I'll work out the next integral, and then I'll erase it again, and then I'll work out the last integral. So you'll need a little bit more space than is available here. Let's go for it. The integral from -4 to 2 of f of x dx equals the integral from -4 to -2 of the function dx plus the integral from -2 to 0 of our function plus the integral from 0 to +2 of our function with respect to x. So obviously I've chopped the entire interval from -4 to +2 into 3 subintervals, and yep, just double checking I wrote those out right. Good. Now, don't overthink this. If I apply the integral here, if I were to integrate from -4 to +2 on that actual function, imagine taking the limit as n goes to infinity of the Riemann sum from I equals 1 to n, right? The limit as n goes to infinity of the Riemann sum, where your, what's the word I'm looking for? What's I in this case? The thing that keeps incrementing up? I'll think of it in a second. Where I goes from 1 to n. And we have our function evaluated at x sub I. And we're multiplying that by delta x. Where we're adding up all the areas of all of these rectangles. The width of each rectangle times the height of each rectangle, where the height of each rectangle is calculated by finding y values. In region A, if we take and turn all of these into rectangles, what can you tell me about the y value associated with the height of each of those rectangles? The y coordinates of every point on this portion of the curve is negative, which means that when we add up all of those negative rectangular areas, we're going to get a negative value. Now, we were told in this problem that A, B, and C all have area of 3, but when we're evaluating an integral like this, we have to be careful when that segment of the curve or the graph resides below the x-axis. So I'm making it negative because it's below the x-axis. And then the next integral going from -2 to positive 0. Put my plus sign so that it lines up with that one. This is a +3, and then my next plus sign lines up, and then be careful, that's -3 again because we're region C is below the x-axis, and we add those up to get -3. I sure hope that's clear, because if you're raising your hand right now, I can't see you. All right, so that is just this integral, integrating our function f from -4 to +2. All right, I need to do some erasing, so give me a moment. And the next thing we'll do is evaluate the integral going from -4 up to +2 of the function 2x. All right, here we are. Integral from -4 to +2 of 2x dx is equal to the I'm going to take this 2 and factor it out. So I'm going to write this as 2 times the integral from -4 to +2 of x dx. And remember that what we're finding is the area under the curve. Okay? -4 to +2. I'm going to draw myself a graph. -1, 2, 3, 4, -1, 2, 3, 4, +1, 2, +1, 2, and I have a very special visitor. Hold on one second. I'm making a video for my students. And he can't hear me because he's got his hearing aids in and his TV program Bluetooths directly to his hearing aids. So draw yourself the graph of y equals x on this coordinate plane, and I'll be right back. So Dad lives with us, and he's 84, and he's 84. Always a pleasure to help him continue navigating the world. Sometimes a little frustrating, but if I've got enough patience for math, I certainly have enough patience to help him get through a day. And I consider it an honor. He's certainly helped me get to where I am today, so if I can help him for the rest of his days, then that's what I'm going to do. And now I'm going to help you for the next couple of minutes in order to finish solving this problem. Hopefully you've already drawn the graph of y equals x. I'm using this point as -4, -4, and this point 2, 2. Both of those points are points on the line y equals x, and I'm going to attempt to draw a nice straight line that connects those, and we want to find the area under the curve. There's my little bunny ears. In this case, we have to be a little bit careful because we want to find this area, and we want to find it. Is it going to draw? Hello? It's not drawing anymore. What happened? Oh, boo. Well, not sure what happened there. So many challenges that life presents us. I'm looking to see if maybe the pen was low on battery. I'm not seeing any notifications coming up. Oh, that's the right side. Yep, Apple Pencil was dead. Okay, so the rest is up to you. Let's see if we can do this. Amazing, I can't just draw with my finger. I can. That was way too excited just then. Okay, we also have to find this area under the curve. So I just finished shading in this region right here. The tricky part about this is that this region over here, as far as evaluating an integral like this, a definite integral, is that this area is going to come out negative. And this area that's above the x-axis will turn out to be positive. So let's find the area of this triangle. Excuse me, it's 4 units wide. It's 4 units vertically tall in the negative direction. And so 4 times 4 is 16 times 1/2, right? Base times height divided by 2 makes 8, except this needs to be -8. And then over here, we've got a triangle that's 2 by 2, which makes 4 divided by 2 makes 2. So you've got -8 and a +2. So you should come over here and write equals -8 plus 2, and -8 plus 2 is -6. And I need to zoom out on this. No. All right, so the value of this integral we just determined is -6. And finally, a little more erasing. We're almost there. You might have already worked ahead and found the answer to the next integral. Do I need to draw it? What the heck? Let's try. No. -1, 2, 3, 4, +1, 2. And what we're graphing is y equals 3. So we need to be up 1, 2, 3 units on the y-axis. And then we can draw our line that passes through. Wow, for drawing with the end of my finger, that was pretty accurate. We need the area underneath this orange curve that I've just drawn. And what we'll end up getting is a rectangle. Wow, that was brutal. No part of any of that was good. I was going to try to do little dots. What we need is the area of that rectangle. It is 6 units wide. It's 3 units tall. 6 times 3 is 18, which means the value of this last integral is 18. And now I've erased everything, so I think the first integral had an area of -3, and then the next one was -6, which puts us at -9, and then this one was 18, so -9 plus 18 is +9. If I recalled those numbers correctly, then I think the answer ends up being +9, or sorry, +9, because this was +18 over here. Oh, that was fun. All right, so those are the problems that I have assigned to my students. I hope that those are some good examples that will help you on your way if you're not one of my students, and I'm glad you got to meet my dad briefly there. Hey, thanks so much for making it through this section with me. I know this was a long one, but there were a lot of important concepts and properties and processes involved in 5.2, and my guess is that those are going to benefit us greatly in 5.3, 4, and 5. I'm just glancing over at the titles of those sections. I see maybe we've got the fundamental theorem of calculus coming, indefinite integrals, net change, and the substitution rule, if those notes are correct. So we'll get to it. I'll see you in 5.3. Thanks so much.